corollary, V separable Banach space, then every sequence in V star has a weak star convergent subsequence. So this is almost immediate, because if V is separable, then and so Fn bounded in V star implies this Fn is contained in some ball 0, radius some capital R, some R, okay, R positive, okay, some but then so let us say B star, which means the ball center origin radius R in B star. So B star 0 R is weak star compact. This is Banach Aloglu, and weak star topology is metrizable since V separable, and in a metric space compactness is same as sequential compactness. Therefore B star 0 R is sequentially compact, that is there exists a weak star convergent subsequence. Okay, so this is just, so in a compact space, in compact metric space, we know that compactness and sequential compactness are equivalent. But in general topological spaces, again one of the arguments why you need nets, filters, etc. is that a sequence may, in a compact topological space, may not necessarily have a convergent subsequence. So examples are difficult to usually write, and here is a nice example which we have. So let us take the space L infinity, which is not separable, which you know. Okay. Okay, so now you define Fn of x equals xn. So this is the nth coordinate projection. So this is x1, xn, and so on. So Fn belongs to L infinity star, and norm of Fn equal to 1 for all. So this is a bounded sequence in L infinity star, and by the Banach Aloglu, B star is weak star compact, and Fn belongs to B star. Okay, so but Fn cannot have a weak star convergent subsequence. Why? Suppose it had, let us just say Fnk converges weak star to some f. Then for every x in L infinity, we have Fnk of x converges to f of x. That means, that is, for every x in L infinity, xnk is convergent, and that is absurd, because you have L infinity is just bounded sequences, and you cannot say there is a fixed subsequence which will always converge, so that you cannot say. This nk doesn't depend on x. Okay, so if you have bounded sequence, you have a convergent subsequence, but that would depend on the sequence, namely x itself. But here I am saying nk is independent of x, and therefore that's not true, and that's absurd, and therefore it does not have a convergent subsequence. Okay, so another example. So why did this fail? Because L infinity is not separable, therefore you cannot apply the previous theorem. Okay. Okay, so now let us take the sequence En in L1. If you take the sequence in En in L1, En of course is 0 etc, 1 in the nth place, 0 afterwards. Okay, so En is in L1, and then so norm of En minus Em 1 is always 2, because if you take En minus Em, you have in one place you have 1, you have another place you have minus 1, and everywhere else you have 0 if n is not equal to n. Okay, so you will have 2, and therefore En has no norm convergent subsequence. But Schur's lemma says weakly convergent and norm convergent subsequences are the same. So by Schur, this implies En has no weakly convergent subsequence either. But C0 star equals L1, C0 is separable, implies En has a weak star convergent subsequence. So implies En has a weak star convergent. But in fact, En itself weak star converges to 0. Why? Because if you take En x, so this is L1 C0. So this is C0 star. What is this? This is nothing but Xn. X equals x1, xn, etc. in C0. And then you know xn has to go to 0 because this. So this implies that En weak star converges to 0. Okay. So we conclude with another important theorem, and this is a cornerstone of many existence proofs in the calculus of variations and so on. Okay, so V reflexive Banach space, then every bounded sequence has a weakly convergent subsequence. So as I told you, weak topology is not metrizable topology and so on. Therefore, you cannot take compact. You know, bounded sets are weakly compact in reflexive spaces, but you cannot take for granted that therefore a sequence will have a weakly convergent subsequence. Just we saw an example of arbitrary. If you do not have metric spaces, you cannot take this. But nevertheless, in a reflexive Banach space, every bounded sequence has a weakly convergent subsequence. Namely, the weakly compact sets have this property in a reflexive space. So okay, so let Xn be a bounded sequence, and you let W equal to the span of Xn, that means finite linear combinations of Xn, and then take the closure. So this is a closed subspace of V. Then W is reflexive, because closed subspace of reflexive space is reflexive, and W is separable. Why is it separable? Because you have this W is the closure of the span of Xn. So every element in W can be approximated as closely as you like by a finite linear combinations of the Xn's, which in turn can be approximated as closely as you like by finite rational linear combinations of the Xn, and that finite rational linear combinations of Xn is a countable set. So every W can be approximated as close as you like by a member of a countable set, or that means W has a countable dense set. Therefore, W is separable and reflexive. So this implies that W star is also separable and reflexive. So that means every bounded sequence in W double star, which is because W star is separable, every bounded sequence W double star has a weak star convergent subsequence, but we are in reflexive spaces, so that is weakly convergent. Because W star is reflexive, therefore the weak and weak star topologies on W double star are the same. So in particular, if you take J of Xn, J is from W to W double star, the canonical embedding, then J of Xn is a bounded sequence, and therefore it will have a weakly convergent subsequence. Okay, so J of Xnk, weakly convergent subsequence in W double star. But J is weakly, so J is weakly continuous, J inverse, J are all weakly continuous, and this implies that X and K weakly convergent in W. But then the topology, that is X and K weakly convergent in V, because this is nothing but the weak topology in W is nothing but inherited from the weak topology in V. Therefore, it will automatically converge. Therefore, you have that this is true. Okay. Now, the converse of this theorem is a very deep theorem. This is due to Eberlein-Schmulian. If every bounded sequence admits a weakly convergent subsequence in a Banach space V, then V is reflexive. This is Eberlein-Schmulian theorem. This is a converse. It's a very deep theorem, fairly difficult to prove. Okay, so we will stop here.